Professor Carlos Frenk, it's such a pleasure and an honor to have you here. Thank you for accepting our invitation. So, you know, like a few days ago, I was opening the newspaper and I saw a massive headline. Most massive super neutron star detected, no? And that made me recall, you know, like a few months before, other headlines, like gravitational waves detected, and a picture of black holes colliding. So it seems that either we are learning more about the universe faster, or there's something going on. Like, what's your view on that?
There are several reasons. It is absolutely correct that the rate of scientific advance, not just in my field and in physics, but throughout the sciences, in biology and even in chemistry, has been unprecedented. But there are many reasons for that. One is, I'm sure most people here realize, there are more scientists alive than dead. So that's one thing, of course, helps.
Volume.
Secondly, well, science is essentially an experimental or observational discipline, and there's been an enormous advance in the technology that allows us to investigate everything from the universe all the way to molecular biology. And telescopes, detectors, they have advanced at an enormous rate, and all of it actually ultimately supported by advances in what many of you people do here, which is computing and all the computing infrastructure that essentially shapes all of our modern technology. So that's one reason. There's only one. Another reason is that as more discoveries are made, it's like the network effect that Google are very keen on. Once discoveries are made, then that elicits more ideas, and people imagine new things. That leads to further experiments. So this is another part of the process. But there are two more that are important. One is enormous investment in science since the end of the war. I think physicists got a very good name after the war. If you live in this part of the world, of course not in other parts of the world, but here I think physicists played a key role and during the Second World War, and that translated into enormous support for science, including physics. But the other one, I think, is crucial, and you see that here. So earlier on, I was just walking around. It's the first time I come to this building, and just listening to people, the variety of accents and clearly different backgrounds. That is crucial. So in the last 50 years or so, the barriers to communication and to exchange of ideas and people have been demolished in the Western world, at least, and even to some extent in China. And so it is this ability of people to move around, to collaborate, to build new enterprises that really is behind this. Just one thing I'll tell you. So there was as you say, there was a big event in astronomy a few weeks ago when, actually now a few months ago, where a black hole ate up a neutron star. Now that produced gravitational waves, and I'm sure you all know about the gravitational waves, but this particular event was interesting because the neutron star was shredded, and then it emitted light in not just gravitational waves, but in many, many wavelengths. And there is a arrangement amongst astronomers that when a gravitational wave is detected, then all telescopes point in the direction of the wave. But it has to do it like this, because so you have a few seconds to point your telescope in the hope of catching something else. And that happened with this neutron star. So if you ever wondered where the gold in your jewelry comes from, it comes from neutron stars like that one. The gold was seen being manufactured there. But the point is that because there were so many wavelengths involved, the paper reporting this merger of a black hole with a neutron star has a third as authors of the entire community of professional astronomers in the world. There's nearly 4,000 people, yes, are authors of that paper. It's a third of the total. So that tells you how science is global and why everybody should be very worried about the tendency now in the world to move away from open borders and to start doing things like building walls and other things of that sort. Well, I'm a Mexican, so.
No, so clearly you alluded at collaboration and exchanging of information and the theories. However, most of us know intuitively that there must be like a series of milestones or grand discoveries or theories that have happened, let's say, in the last 100 years that had made possible everything else. What in your view, are the key building blocks of knowledge that have allowed us to get where we are?
Well, if we go back 100 years, of course, the two pillars of modern physics are only 100 years old. Another pillar, of course, is 350 years old. That's Newton mechanics. But modern physics began really with quantum physics, quantum mechanics, that is only about 100 years old, and the theory of relativity. So these two are the great scientific breakthroughs that brought in a new era in which we which we are now able to understand a lot about the intimate details of the universe. So what I do, I worry about the universe. So let me tell you about the breakthroughs in cosmology. Yeah. The next one, I would say, although some people would take issue with that, but let me skip the discovery or the inference of dark matter. We're going to talk about that later. But in 1965, actually, this is very interesting. Two engineers, in fact, who didn't work at a university, who worked at the equivalent of Google in those days, at Bell Labs in the US, discovered the Big Bang accidentally. So they didn't set out, they didn't know the Big Bang had happened, and they discovered radiation in the form of microwaves that was coming from everywhere in the universe. They were very annoyed because they were trying to build a telescope to do radio observations of the sun. And they couldn't calibrate the telescope because they pointed away from the sun, and there was this signal. They pointed everywhere they pointed it, and what they had discovered unwittingly was the Big Bang. And in particular, they discovered the heat left over from the Big Bang. So our universe began in a very hot and dense state, and it's been cooling ever since. And because it's rather old, about 13.7 billion years old, the radiation has cooled to wavelengths that can be measured in microwaves. And so Penzias and Wilson, who of course got the Nobel Prize for this, had the first evidence that our universe began with the Big Bang. So that was a milestone. And then the milestones, as you say, have been coming thick and fast. The next, I would say, big breakthrough was when a NASA satellite called COBE was not only able to measure the properties of this radiation in great detail, but discovered that the temperature of this heat was not the same in every place. So there were small parts of this radiation that were slightly hotter than others. And that doesn't sound like much. You know, you see the window there, you say, well, there are lots of drops. What does that tell me? Well, this pattern of hot and cold spots told us how the universe began. And we can elaborate upon this later, but that is the blueprint for how the universe was created. And we could see in this pattern physics that happened when the universe was a tiny fraction of a second old, 10 to the minus 35 seconds old, which is when the origin of these hot and cold spots were established. And as we will probably talk about later, that's where you all come from, by the way, this little pattern of hot and cold spots. So that, again, won the Nobel Prize to an old friend of mine from Berkeley, George Smoot. That was another big breakthrough. What they discovered was the universe, our universe, we know it's been expanding since Hubble, but not only is our universe expanding, but the expansion is getting faster and faster and faster. So the universe is accelerating. Now, so what's the big deal? Well, the big deal is that until then, we thought that all the universe contained was matter. And as Americans say, gravity sucks, meaning gravity pulls things back. So if all the universe contained was matter, then the expansion should be slowing down because the matter would pull it back. But the discovery was the opposite. The universe is expanding faster and faster. And that is caused by something that we know so little about that we've given it a mysterious name, dark energy. So if you want to get a grant, talk about dark energy and you're already got a good start. So we don't know what it is that is causing our universe to accelerate. We think, and after I finish this sentence, you will know as much as the experts in the field. We think it's something to do with empty space because most of the universe is empty. So, I mean, when we look at, there's lots of stars, and if you've ever been to Mexico, which I recommend you go to the south, you see the Milky Way, the sky is full of stars. Actually, the universe is mostly empty. It's It's mostly empty space. And there's something about this emptiness of space that is pushing galaxies, making them move farther and farther apart. So that's called dark energy. And that was, I would say, the last of the three major advances that have allowed us to reconstruct, using computers, the whole evolution of the universe. So that is not a discovery as such, but the ability to deploy high-performance computing in real anger, which is what we do, to try to piece together all these bits of information. That is also a key in the way in which we have advanced in our knowledge of our universe.
You're being a little bit humble, Professor Frenk, in the sense that in the milestones, you alluded to cold dark matter and you skipped it, but a lot of people would agree that actually your theory is one of the milestones that have allowed us to get where we are. Why don't we talk about it? But first, if you could level the playing field, level the knowledge, and please tell us, as you will tell your grandson, well, at least that would help me. Dark matter, like, what is it? Why cold dark matter? It implies that there's some other flavors of it. And why is it so important?
Right. Yeah, no, I wasn't trying to be humble, but by the way, my grandson is only 2.5, so he likes.
Okay, well, 5.
He likes to talk about other things, but anyway, so like what he's going to have for lunch and that kind of thing. But so one very interesting thing, when this pattern of hot and cold spots was discovered, I hinted that it told us a lot. Well, amongst the things it told us, and this is, I think, a real breakthrough, is what our universe is made of. Now, we've known actually since a Swiss, very grumpy astronomer called Fritz Zwicky in the 1930s, that there is something in the universe that doesn't kind of add up, which he called dark matter. I'll tell you more about it in a minute. But dark matter has been there, but these hot and cold spots of the, let me give it its technical name, it's the microwave background, or the cosmic microwave background. This pattern of hot and cold spots allows us to decode what the universe is made of. And now we know exactly that our universe is very bizarre, and it exactly has about 25% of what the universe contains in energy, if you like. For those of you who are physicists or engineers, about 25% is this dark matter that Zwicky knew about. About 5% is what we are made of. The ordinary atoms of the periodic table, hydrogen, helium, carbon, oxygen, gold, and so on, that only makes up 5% of what the universe contains. 25% dark matter, 5% ordinary matter, as we call it, and the rest is this dark energy, this 70%, this mysterious dark energy that's pushing the universe around. Now, so the dark matter had been known since, I'd say, the 1930s, but it was only when cosmologists began to try to make sense of a variety of observations that it fell into place. So in the 1980s, when I was a young postdoc in Berkeley, which I remember that was so much fun. Even the police had long hair, but that was before. Anyway, so there came a really, really heretical idea, which it didn't make any sense at first, and now is the pillar of the cold dark matter theory. I mean, there were two ideas, to be precise, but the first one that really took everybody by surprise was that it was at this point just a theory, a hypothesis, simultaneously put forward by somebody in the United States, in the MIT, Alan Guth, and in Moscow, Andre Linde. They didn't talk to one another because in those days it wasn't easy to talk across the Iron Curtain. But the two of them at the same time came up with the notion that when our universe had just come into existence, 10 to the minus 35 seconds after the Big Bang, it was caught in a funny state to do with quantum physics. So there's something called quantum fields. You all know about the Higgs boson, but the Higgs is a quantum field. It's to do with the microscopic fabric of space. Now, the idea that these two people put forward, and they won many prizes for that idea, was that when the universe began, it had a quantum field, and that quantum field was caught in the wrong state. The physicists call this a false vacuum, but don't worry about that. What happened was the universe expanded very rapidly over a very brief period of time. It's called cosmic inflation. But the main thing was that because there are quantum phenomena involved, then quantum phenomena fluctuate. And these phenomena, as the universe inflated, gave rise to the appearance of small inhomogeneities in the energy of the universe. Some bits were more dense than others were less dense. Now this, we now understand, is the origin of the hot and cold spots in the microwave background. But not only that, it is the origin of everything we see in the universe. So idea number one that was heretical, although, you know, very enlightened people, like the reason I came to this country was because I met one of the greatest minds, I think. If you ever have a chance to see this man speak, you can find him in any number of, just go on Google, as I presume you do all the time, like we do, and put Martin Rees. He's the one who brought me here. But so the, what was I saying? Yes.
The heretical idea number one.
I was a student at the Institute of Astronomy in Cambridge, and there was this paper called Cosmic Inflation. This is 1980, when in this country there was Margaret Thatcher and there was a lot of inflation. And I said to Martin, is this paper serious or is it just a joke? And Martin, who's now Lord Rees, says to me, look, that piece of paper you're holding in your hand may well turn out to be the most important piece of paper you've ever touched. And he was right. I don't know if any of you have ever touched a piece of paper that makes you think, well, maybe this is some game changer. Well, that was it. So the modern view of cosmology is that the universe began with these quantum phenomena, seeded the universe with small perturbations in the energy density that are reflected and seen in the microwave background. Then heretical idea number two, which actually originated from behind the Iron Curtain, that was that the dark matter that Zwicky knew about could be made of elementary particles, that is subatomic particles, completely different from the particles that make ordinary matter, like atoms and molecules and so on. They're the ordinary matter, the 5%. So here, the proposition was that the dark matter was made of hypothetical particles that were very different from ordinary matter. And the reason they're dark is because they don't collect into atoms, they don't interact, they just produce gravity.
We don't see them, therefore.
We don't see them. If I'm right, and the dark matter is what I think it is, and many others think it is what it is, this room is full of these dark matter particles, but they just go through our bodies, and we don't feel anything because they don't interact. And so they're not harmful at all, but it makes them very difficult to find because you put a detector and just go through and they don't interact. Well, you're none the wiser. So, but here comes the beauty of the whole story. The idea was that the dark matter, in the form of these hypothetical elementary particles, would cause those small ripples from inflation to be amplified in the following way. So if because of this quantum phenomena, this patch of universe turned out to be denser than average, well, initially it was expanding, but because it had more matter than the surroundings, then eventually it would stop expanding and collapse and produce an object that would later turn into a galaxy. So this was the key idea. Inflation, quantum fluctuations, and amplified to macroscopic scales by the action of gravity, which is the weakest of all forces. However, the universe is old enough that there has been enough time for these small perturbations to collapse and produce objects like those we see in the universe around us. Now, so where the cold dark matter comes from is that particle physicists very soon realized that the details of this patchwork of hot and cold spots would depend on the way in which these particles moved. So cold dark matter are very slow-moving particles. There was hot dark matter, which were very rapidly moving particles. They move at relativistic speeds. The neutrino, most people here would have heard, I imagine, the word neutrino. Well, they were candidates for hot dark matter. And the first work I did in Berkeley in the 1980s was to rule them out by using a new technique that had been invented then, whereby we could, the story I've told you, we could calculate it in a big computer.
Is that where simulations and simulating universes and galaxies come
That's where it
into play.
came into play, yes. And I mean, the computers we had with which we ruled out hot dark matter were laughable by today's standards. So I remember in Berkeley, so in the winter of 1981, until then, the Department of Astronomy in Berkeley had a computer called a PDP-11. I don't see anybody old enough here to remember PDP-11s, but anyway, oh, you do. So there was a breakthrough in computing, which actually was the mind behind this breakthrough was a former Google vice president, Wayne Rosing, whom I met. He was a key part in the development of these computers called VAXes. Beautiful computers, much better than all this Unix stuff that we have today. Anyway, Berkeley acquired a VAX 780. Now that blew everybody's mind. It had an incredible 4 megabytes of memory. Now can you imagine what you could do with 4 megabytes? Well, now, so I just arrived in Berkeley, and being Mexican, and Mexicans are very good at taking advantage of opportunities and improvising, I thought, I'm going to learn how this computer works before anybody else. And then they will go on holiday for Christmas, and I can use it by myself. And that's what happened. And that's where the first simulations of cold dark matter were done during the Christmas break, 1981-82, thanks to
4 megabytes.
Oh yeah, there were 4 megabytes. It's laughable today. But the thing that my collaborators like to boast about is that even though we had 4 megabytes, we were doing simulations. Simulations, you have particles. And the particles represent all the matter in the universe. But the universe is very big. So we had to represent the whole universe with 32 cubed particles, 32,768. That was all. Today, we do simulations, and we're just doing one in China with 1 trillion particles. Yet, let me just say, nobody has found anything wrong with those previous first simulations. Yes.
That's called craftsmanship.
No, but it's called good luck.
So tell us about, that's interesting, supercomputers, no? That brings to mind a lot of concepts, no? And probably everybody has a different definition of supercomputer. But you use them every day for your work, and your work depends on that. Can you characterize for us what qualifies a supercomputer today in your field?
Okay, yes.
What is it, and what does it do for you? All the calculations, the rendering?
Oh, well, what we call a supercomputer is one that has many cores. Mm-hmm. So, I mean, even my watch probably now has a few cores, but so to be a supercomputer, to be respectable as a supercomputer, you have to have at least, I want to say, a few thousand cores. He knows. Yeah. He ran one of our supercomputers. A few thousand cores. But now the new ones have 1 million. So it has to have lots of cores. But the main thing is, in order for it to be high performance computing, you have to get them to work together. So it's no good having 1,000 different independent processes. That's actually called, we want to do something called massively parallel computing, and which requires the different cores to communicate with one another and to work together. So that's what makes a supercomputer. It's a large number of cores, all programmed using parallel type software to work in unison, to work together. And nowadays, if you want to get time in a big supercomputer, you have to show what we call scaling, that as the problem gets bigger and you want more cores, then your code runs faster than it would otherwise. So that's supercomputers being crucial. Cool. And I think in cosmology, we were some of the people who got lucky that we began using supercomputing in a very, very extensive way. But supercomputing now pervades all of science, really, not just my science, but other disciplines too.
Could you give us a sense of, let's say, any given simulation that you do? Does it take days? Does it take months? How does it work? Once you press go, what happens?
You go on holiday and you wish that you hope that when you come back it's done. Now, So there are many simulations, there are many types of simulations. So they're the big ones where we really try to understand the universe on large scales. And then there's smaller ones where we want to understand, for example, we know the Milky Way is part of a group of galaxies called the Local Group. And if we want to understand the details of our own environment, then you do a different kind of simulation. If you're interested in the dark matter, you do easy simulations where only gravity plays a role. If you want to understand where the stars come from, and I'm sure one day we'll ask the questions where people come from, but at the moment we stop at stars and planets. Then you do a different kind of simulation. Now the big ones could take months. So you don't do those very often because your students get impatient. But typically you could wait 3, 4, 5, 6 months for the simulation to finish.
And is that continuously running?
All the time. Just keep the machine busy. And yeah, I mean, my colleagues and I are among the most unpopular people in the computing world because we kick everybody else out of the computers and we just use them. And we say, look, we're trying to simulate the universe. For goodness sake, give us a break. I have my thesis to finish by next Thursday. So we're not very popular, but that's what you need. You need to be able to do that.
And you have here in the audience probably, and in this building, as I was telling you before, a lot of colleagues involved in either machine learning techniques or in artificial intelligence. Do any of these play a role in your techniques, in the techniques that you use?
Yeah. So let me say something slightly provocative. We've been using these techniques for 30 years at least. We just didn't call them that. So it's like the dark energy. You come up with a nice name and then you can make lots of money. So artificial intelligence, well, let me be more precise. So for example, neural networks, which is one of the techniques of artificial machine learning. Principal component analysis. I was doing that when I was a student in the 70s. Now, but we didn't call it artificial intelligence or machine learning. Now, of course, that was laughable. That was like my 4 megabytes compared to what artificial intelligence machine learning can do today. And that's because the amount of data around that you all know all about is just mushroomed as has the computing power. And so now the machine learning is just so much more sophisticated and powerful than it has been in the last few decades. But the techniques, the basic techniques, well, they're simple statistical techniques. They're well understood, well known. But of course, now we use machine learning all the time. And because like in many other parts of human activity, astronomers now generate enormous amounts of data. And and in order to find patterns in this data, just like you do in many other applications, we use an increasing number of applications of artificial intelligence. I think most of my students now will probably do during their studies projects involving machine learning for sure.
Artificial intelligence.
Yes, because we get terabytes of data, even from the simulations, let alone the real universe. But we now have a new generation of telescopes that it's just amazing. I mean, for example, there's a satellite. People know this called Gaia out there, launched by the European Space Agency. That is just interested in our own galaxy. It's not interested in the universe as a whole, just our own galaxy. But it's going to make measurements for 3 billion stars, which is about 1.5 billion stars, which is about 3 billion stars, which is about 10% of all the stars in the Milky Way will have been observed by the Gaia satellite and have properties measured. Now, and that's small by the standards of the data sets that we are going to acquire. There's a big international enormous telescope called the Large Synoptic Something Telescope, the LSST. That is going to generate in one day as much data as the Large Hadron Collider generated, I think, in a month or something like that. So, of course, without machine learning, you don't advance. So yeah, we use that all the time, and so I encourage people here who do machine learning, come up with more stuff. We love it.
So now, Professor Frenk, if you had like your magic wand, your 3 wishes, like what 3 mysteries out there in the universe would you like to either for you to solve or for science to solve in your lifetime?
I hadn't anticipated this question. It reminds me once I was doing a program on cosmology for the BBC.
Yeah.
And we were filming in Durham. Durham is hilly. And I used to smoke in those days. I'm glad I gave up. But they wanted me to go up and down this hill. After twice, I could hardly breathe. Anyway, so I was walking backwards of the hill. And then the producer says to me, last question. If God came down and you could ask him one question, what would it be? They're choking there. And the question I ask has been answered, which is, what is the value of the mean density of the universe? Now, that might sound silly to you and very technical, but that had the key to understanding the whole evolution of the universe in those days. Now, we answered that question. We know what the density of the universe is, because we now know that we have, the 5% of ordinary matter, et cetera, et cetera. So that question's been answered. So I think now the questions are less general than that one. I would say there's three questions in my mind. One, are lumped together. What is the dark matter really? Because we know the dark matter has to be there. Otherwise, the universe doesn't make any sense. Our simulations look so much like the real universe that there's got to be something in the universe that it's like what we simulate. And I can make universes that are a disaster. So you just change slightly the properties of the dark matter or the expansion rate or something, you end up with disasters. I mean, you could easily annihilate the whole universe, kill off our galaxy. You got to get it right. So I think that but the reality is the dark matter is a hypothetical concept. Nobody has yet come along to a press conference saying, here, I've got you an elementary particle that is a dark matter. So that's mystery number one. What is the dark matter? I'll put together with it what is the dark energy, although they're very different things. So I think my generation should, I hope, discover the dark matter. And I say, well, in the next, say, 5 years or so, but I've been saying that for the last 25, but ignore that. So I think the dark matter is a soluble problem. The dark energy, I don't know where that's going to, the solution to that going to come from, because no theory of physics, so just backtrack a second. The current idea is that the dark energy is something that Einstein introduced in his equations called the cosmological constant, which he introduced for the wrong reasons, and then he took out and said, this is the worst thing I've ever done, is talk about this. Yeah?
Like he was fudging this.
Well, I mean, the story is that, so when Einstein, this is a beautiful story, when Einstein wrote down the theory of general relativity in the 1920s, a priest, actually, Georges Lemaitre in Belgium, and a Russian mathematician, the priest was called Georges Lemaitre, and the Russian mathematician, Alexander Friedman, they solved the equation that Einstein hadn't solved, and they wrote back to Einstein saying, Mr. Einstein, sorry, you're wrong, because your theory predicts that the universe should be expanding. And as far as we can tell, it's not expanding. The expansion of the universe was only discovered in 1926 or 27 by Edwin Hubble, and this is before that. So Einstein said, oh my God, my theory predicts an expanding universe. We don't see the universe expanding. Let me stop the expansion by adding this constant, which you are allowed in physics to add constants because it's the way physics works. You can add energies here and there, and you still get paid at the end of the month. So Einstein added this constant. And then he went, met Hubble. Hubble said, look, the universe is expanding, Mr. Einstein. And Einstein said, oh my God, took out the cosmological constant and said, this is the biggest blunder in my life. Now, what can cause this accelerated expansion is Einstein's constant, but with a different sign. So Einstein introduced it to stop the universe expanding. Now we want it to expand faster and faster, have the same constant, change the sign. But that is not really science. I mean, it's not. So the dark energy is a fundamental problem. It tells us about something very deep about our universe. I don't think I'm going to solve the problem. I don't think my students are going to solve it. Who knows who's the solution? So that's question one. Sorry, I'm taking a bit long. Question two is, are we alone? Is there life elsewhere? And to me, that's a profound question as you can ask. I feel, this is my own personal opinion, there's no evidence. I'm just about to give you an unscientific statement, not backed by any evidence at all. But to me, it seems quite likely that the universe must have lots of life, but primitive life, bacterial life. That about 90% of the biomass on Earth, which is the only place where we know about life, is bacteria. So that seems to me fairly reasonable that the universe has bacteria. We see in telescopes the building blocks of DNA. They're all over the place. So I don't think that's so hard. But the key question there, is there intelligent life somewhere else? And that I've no clue whether the answer is yes or no. But I do know one thing. We have the technology in place, and this will be the next big thing after the gravitational waves. The dark matter, the next big thing is going to be you wake up in the morning with a big headline, evidence of life has been discovered in a nearby planet. I think that's the next big thing coming, and the technology is there. So it's actually quite straightforward.
It's a matter of time and effort and luck.
Luck, of course, but the technology exists. It's just telescopes that measure the atmosphere. And then the third question, that again, I don't know who's going to answer that, and that is, we know our universe began with a Big Bang. We have lots of empirical evidence for that. So that's not an issue. The big issue is what went bang. And that, I think, to me, is a fundamental question, and I have no clue how we're going to answer that question.
Thank you. Professor Frenk, before we hand over to our audience, which I hope that there are some questions floating around, for those that perhaps know about your work but know less about you as a person, you were alluding before to something very interesting, which is, multicultural backgrounds and how that has played an effect, a positive effect. You were born in Mexico and you studied in Mexico, then came to the UK in the 70s. What do you think, if at all, that from that background, that upbringing, that cultural packaging has influenced you the most in your work?
Well, I think one thing I learned growing up in Mexico, I already made a mention of this. So Mexico, of course, is not, and it wasn't even more so then, a rich country, full of resources, and you have to do what you want to do with limited resources. So the Mexicans are the masters of improvisation. I remember, every time my car broke down, I was so amazed how the mechanics would bring one bit from here, a wire from there, borrow a string from there, a piece, and get my car going again. So this would never happen in this country, and it would never here. You have a little dent in your car, and they make you buy a new one. So improvisation is one key element. Flexibility, imagination. So the Mexican culture is hugely imaginative. We see that in so many ordinary walks of life, from the architecture that is wonderful. So if any of you ever go to Mexico, don't miss the university. It's called University City. It has some of the most magnificent buildings that you can imagine. And studying there, of course, you absorb this, but it's creative. The Mexican literature is just full of genius. I mean, the most surprising, unexpected things happen in Mexican literature. There's a very famous movement when I was there in literature in Latin America called magical realism.
Oh, yeah.
Well, the Mexicans, although the Argentinians get the credit for this, but it really is the Mexicans who are both magical and realistic. So that's the other one. You see it in the music, you see it in the humor. The Mexicans have the most strange humor that not even the British actually understand.
And that's a statement. That is a strong
subtle.
statement.
It's ingenious. So that's one thing I learned. The other thing I must say, I went from Mexico to Cambridge, and the standards of my lecturers in Mexico were so much higher than the Cambridge lecturers.
Controversial.
I remember thinking, I go all the way here to the rain and the cold, and I get these lectures were not half as good as the ones I had in Mexico. So, of course, there's more to being a scientist than just listening to lectures. So the university, I don't know now because I've been there for a long time, but the standards of the University of Mexico were very, very high, the intellectual standards. And of course, because they didn't have many resources, they were mostly geared towards theoretical thinking, mathematical thinking, because we didn't have the equipment for experiments and so on.
Yeah.
So if you ask me in one word what it is in my cultural heritage that really influenced me, was this ability to improvise, and for that to be imaginative.
Be resourceful.
Yes, resourceful and imaginative. And never take no for an answer.
Determination. Some will call it stubbornness, but determination.
I'll get your car on the road again.
So I would like to hand over to our audience.
Thank you very much. That's a beautiful conversation, and it's lovely to hear more about the mysteries of the universe. It strikes me there are so many things that are so beautifully woven together in the universe that that just seems like it's unlikely that it was just an accident. What do you ascribe to the beautiful balance that seems to be holding the universe together and where we are today? What's behind that?
Well, thank you for that question. So I'm sorry to disappoint you. I don't have the answer, but I do have. I think your question is very profound, and let me tell you what to me is the biggest mystery. I mean, I've been dealing with the universe all my life, and to me the most mysterious aspect of the universe is this: that it conforms to what we call the laws of physics. Now, so the laws of physics are laws like Newton's gravity and so on, that are discovered almost invariably. There's one exception I will come to in a minute, in laboratories here on Earth. So most of science, most of physics comes out of laboratories. Newton's theory of mechanics, and everything comes from experiments, except relativity. I made the statement once at a talk that everything was empirical, and then somebody said, no, relativity didn't come from an experiment, it came from Einstein's head. Fine. However, the laws of physics are all discovered here on Earth. And yet, they seem to apply not just in Earth and our laboratories, but everywhere and at all times, even in conditions that bear no resemblance at all with the conditions in which these laws are discovered, like the Big Bang. So the densities, the temperatures of the Big Bang have no parallel. And we don't even need to do what happens in our laboratory. We don't even need to go to the Big Bang. The gravitational waves. I mean, a neutron star is the mass, it's like bigger actually than the mass of the sun, in a volume smaller than London. Now, those conditions are impossible to replicate in the laboratory, and when we study them with the laws of physics, they apply. So why are the laws of physics universal? Why does the universe know to respect relativity, to respect Newtonian mechanics, to respect electromagnetism? That, to me, is the biggest mystery. And unfortunately, I don't know the answer to that question, but I think that's what you're getting at. And I wish I would know more of how to answer this in a more conclusive way, but to me, it's just the biggest mystery. In fact, sometimes keeps me awake at night thinking, well, why is the universe? I mean, of course, if it wasn't like that, we probably wouldn't be here. If the universe was chaotic and there were no rules, well, you couldn't play the game if there aren't any rules. So some people might say, well, it's just an anthropic thing, that the reason we're here is because these laws are universal. But that I don't find a satisfying explanation. Yes, no, thank you for your question.
So you mentioned that one of the questions you'd like to get answered is about the other forms of life, especially the forms of intelligent life out there in the universe. So my question is around, I don't think we have, as a humankind, right? I don't think we have come even to answering the philosophical question, what is the fundamental difference between something we call alive and not alive? So how is fundamentally a rock different from a bacteria? I've experimented finding answers to that question, like, is it replication, is it feeding, is it something else? But it's all easily refutable. So there is no criterion for that, and yet, so I mean, even if we do not distinguish something alive and not alive, then how can we distinguish the other question is intelligent life from not intelligent life?
Great question. So thank you again. These are things that preoccupy me a lot. Now, so I should have qualified when I said what I said, that I was talking about life as we know it, not life as we don't know it. Now, there could well be lots of life as we don't know it. In fact, it may well be that the future of our species, maybe there is a post-human fate for our descendants, where you can hardly tell the difference between what we call humans and computers. I mean, if you extrapolate the incredible advances in computing, you could easily imagine, and the way in which computers are increasingly becoming part of our mind, we extend our mind. So one of the many things are bad when you grow old. One of them is you forget names. I don't care anymore. Or I get lost. I don't care. I get my phone and Google tells me. So Google is an extension of my mind. Now, the moment it's in my pocket, well, in the not too distant future, it might be inside my cranial cavity for all I know. So it may well be that our descendants will be more like computers than humans. Would we still call that life? Well, that is a question of definition. To me, and that's my own personal opinion, the key element of life is the ability to evolve and to transmit genetic information from one generation to another. But that's just my own definition of the key for life. But I don't think I agree with you. We don't have an objective definition. But when I was talking about the search for life, I really meant life as we know it. And I think life as a metabolic activity, what we call bacteria, I think that we know how to, in principle, discover. But I think there will be a problem, of course, when we do one day have some signals from somewhere. How do we know it's intelligent or not? So I think those are open questions.
Hi, thank you for a fascinating conversation. I wanted to actually ask a question based on what you just talked about your extended mind, and how I wanted you to reflect on how the changes in computing and the sophistication of your simulations have changed, or maybe they haven't changed, your intuitions over the years and your creativity. Has there been a change in the way that you work with computing and simulation has affected your thought processes or your intuitions, or have they stayed the same?
Oh yeah, no, this is a really good question too. So what's happened in my own field? It was transformed by computing because of the ability to do simulations. Now the simulations themselves, when I started, output was just a bunch of numbers. But now we can make representations of the simulation, visualizations, where you take all these numbers, put them together, and you can make a movie. And in fact, Salvador says I'll show you a movie later when we finish.
By the way, there's for those who would like to see, we're going to try to. Professor Frenk graciously brought one, and 15 minutes after the talk, we can stay a little bit and see some of the simulations.
So the ability to visualize the output of a calculation. So essentially, what a simulation does is very straightforward. You start from some initial condition, which is what we learned from inflation, dark matter, and so on. And all a simulation is solving the equations of physics. So if you're interested in dark matter only, in your simulation, you only solve the equations of relativity and gravity. If you want to be able to simulate other things like stars and planets and so, then you need to put in more complicated physics, but the equations that regulate those physics are understood, and all the computer does is solve the equations. Now, however, so which is what physicists do, but there's an enormous difference between solving an equation with pen and paper and solving it in a computer, especially these complex processes that you can then visualize. So have 40 years or so of working on simulations changed the way I approach science? Absolutely, completely. My imagination's been stimulated constantly by seeing images of primitive galaxies, seeing, the universe actually, sadly, I'm sorry to tell you, it's a violent place. There's all sorts of nasty things go on out there. In particular, galaxies collide. And when they collide, all sorts of nasty things happen. And to be able to see collisions, for example, I'm very interested in what's going to happen to our own Milky Way. It is on a collision course with our neighbor called the Andromeda Galaxy. But before that, we're going to get hit by another galaxy, which I first saw in Mexico, in fact, in hiking in the south of Mexico. It's called the Large Magellanic Cloud. You only see it from the south or from the tropics. Anyway, that is going to collide with the center of our Milky Way. And so visualizing all these things has enriched my life as a scientist enormously. But of course, I'm very privileged in my subject where we can do this. I always feel so sorry for particle physicists who, what can they do? You see these things colliding and making a little splash. Well, that's nothing compared to the movies that we make for a living.
You're Hollywood compared to...
Well, absolutely.
Any other questions? So if I may repeat for the video, the question was, In order to search for the existence of life, should we focus in our solar system, in our galaxy? Should we venture further afield? And what would be your approach to go about it?
Well, I look everywhere. You know, if you lose your keys, you look wherever you can. But I think just in response to the question, we're looking for life as we know it. So we know that water is, as we say in mathematics, a necessary but not a sufficient condition for life. For life as we know it, in addition to water, you need to have the right temperature. You need to be in what astronomers call the habitable zone of the planetary system. Now, I think we're pretty certain that the solar system doesn't have intelligent life. Maybe nowhere, maybe not even on Earth, but I think we do have it on Earth. But there could be bacterial life, there could be primitive life, either in vents, where even though the planet is too far away to be at the right temperature, but for instance, a good place is well, Mars is a reasonable place, but the moons of Jupiter, for example, they are heated by very interesting gravitational phenomena, so they could harbor primitive life. I think if there was more advanced life, we would know about it. So the one other thing that we didn't really talk about, where there's been a tremendous advance in the last 10 years or so, is in discovering planets outside our solar system that are just like the Earth. When I started as a student, the only planets we knew about are in the solar system, and now there are 10,000 or so planets called exoplanets orbiting other stars, not the sun, and there is a subset of those which is much smaller, but just a few tens, where conditions are like in the Earth. So these are in the habitable zone. They're called Earth-like planets. In fact, recently in the news, there was something called a super Earth, which was a very nice planet that looked just a lot like Earth, except it was much bigger. But not that much bigger, somewhat bigger. But so I would look there, because if we're after life as we know it, then the first thing I would try to find out is whether these planets have an atmosphere. And we can do that in a way which is now possible, because when the planet goes in front of the star passes through the atmosphere. And with sufficiently sensitive detectors, you can analyze the light from the background star and look for signatures of life. And in fact, it turns out that life is what we call a non-equilibrium process. So oxygen, for example, generation of oxygen. So the abundance of oxygen, it's changing all the time because we breathe and then the oxygen gets metabolized. And so the existence of oxygen is a non-equilibrium process, and you can tell if an atmosphere has oxygen just by seeing how the light from the background star is absorbed by the atmosphere. So that's why I was saying before, the technology is there. So I would drop everything anybody else is doing and go and make sure we have the telescopes. You probably have to do this from space, and the detectors to be able to analyze the light as it goes through the putative atmosphere of an exoplanet. So I would put a lot of effort there, but I would still continue looking in our own backyard, because I think even if we don't find, as I don't think we will, intelligent life in the stars, just finding any evidence of life outside the Earth would be such a transformation to everything. Just like the way in the Renaissance, where the realization that the Earth goes around the sun changed all of society. It changed the way people did art. It changed the way people looked at themselves. It changed the philosophy of the time. I think likewise, discovering life outside the Earth would be as much of a cultural revolution, artistic revolution, and psychological revolution as the discovery that the Earth goes around the sun. So no, I think this is clearly hugely important quest.
Well, it is with the quest of life that we get to an end of our very, very delightful talk. Thank you so much. If you could just join me in thanking Professor Frenk.